All right. So do you think you're ready here, Enoch?
Yep, as ready as I'm ever gonna be after that.
Okay.
All right, we just. We'll send it full screen here. There we go. All right.
Okay, go for it.
All right, so hyperbolic trigonometry and area. At first, we might think these are two unrelated topics in math, and maybe that's what it looks like at first glance. But there are intimate connections between them that we probably might not see if we don't actually take a deep look. So the problem is oftentimes, like calculus textbooks, we will have a basic analytical understanding of these hyperbolic trig functions. And so that can leave us with a bunch of unanswered questions. However, what we're going to see here is taking a geometric approach will help us understand more about this. So in this presentation, we'll first of all look at an overview of hyperbolic functions. And then we are going to get to the area approach, the geometric understanding. But before we do that, it's helpful to look at polar trig functions, such as sine and cosine, and see the relationship between polar and hyperbolic trig. And only then can we actually parameterize by area, first with the polar trig, to show why that works. And if that does work, which it does, we will be able to go into hyperbolic trig and do the exact same thing. And once we know what the area formula is for hyperbolic trig, we'll be able to discover answers to questions like, okay, why are the formulae for cos t, or hyperbolic cosine of t, and sinh t, the hyperbolic sine of t, why are those formulas written the way they are? Why exponentials, factors of a half, etc. And from that, from the understanding of area, we'll be able to find the integrals for the inverse hyperbolic trig functions. And once we do that, we can find the derivatives of the normal hyperbolic trig functions, sinh t, cos t, without using any of the analytical understanding behind it. And so we're going to come at it in a totally new way. And finally, we'll close with looking at an intriguing extension into a different type of geometry. So first of all, what are the hyperbolic functions? So these are based on the unit hyperbola x squared minus y squared equals 1 with x greater than or equal to 1. Up here is the graph of the unit hyperbola x squared minus y squared equals 1. As you can see, it opens to the right and to the left, has vertices at 1, 0 and negative 1, 0, and it has asymptotes. And those asymptotes are going to play a very important role as we get further along into this presentation. And for right now, we're going to stick with just the right branch of the unit hyperbola. We're going to define a point x comma y on the unit hyperbola, an arbitrary point, as x equals cos of t and y equals sinh of t. And now we could dive straight into area, but first I want to take a brief pause to refresh our memory on polar functions. So as you can see, the polar functions are based on the unit circle x squared plus y squared equals 1. We define the polar functions as x equals cosine of t and y equals sine of t, thereby giving us our points for the coordinates. As you can see from what I said earlier, the hyperbolic functions look pretty similar, but there are some key differences, such as that negative sign between the x squared and the y squared, and also just how we define them. Notice they're cos t, sinh t, not cosine of t and sine of t. And from our analytical understanding of hyperbolic functions, as we see from textbooks, we see that cos of t is defined as 1/2 of the quantity e to the t plus e to the negative t. And sinh of t is equal to 1/2 of e to the t minus e to the negative t. Now, we're going to come back and revisit why those formulas are what they are later on. But first, I want to get us thinking about area. So normally, just at first glance, if we saw cosine of t, sine of t, how would we think about them? Well, we might first of all say, wait, could the argument t represent the angle measured in radians? Because that's what we've been taught to think like, oh, cosine of pi over 6 is like √3/2. And then from that, we get coordinates once we know the angle. So while that might seem like a great idea at first glance, when we try to transfer this understanding into hyperbolic trig, it just doesn't work. And why not? Because remember, on the graph of the hyperbola, the unit hyperbola, we see that there are asymptotes. And so therefore, we cannot get angles of pi over 4 radians or above that. So now we're stuck. But wait, is there some other way we can approach it? Well, it turns out we can if we try this area parameterization approach. Now, this approach has been known since 1895 by a mathematician by the name of M.W. Haskell, who wrote a paper on the intro of the notion for hyperbolic functions. And so this hasn't been looked at in great detail until Dr. Hammett, together with John Engbers, looked at it and saw how this could be applied to hyperbolic trig functions. So how can we be sure that this will work? Well, let's go back to our polar trig and figure this out. So we first of all consider the unit circle, which is a circle centered at the origin with radius of 1, and a circular sector, which is formed by taking an arbitrary point x comma y on the unit circle and drawing a line from there to the origin. And then from the origin, we go out to x equals 1. And then the area inside it we shade, and that is our sector. So we're gonna let theta over 2 be the area of the circular sector of this unit circle. Now, that might seem arbitrary at first. After all, why go with theta over 2? Well, here's a brief explanation of that. So remember when we studied circles first, we noticed that the area of the sector is A equal area equals pi r squared times theta over 2 pi, where A is the area and R is the radius of the circle. And remember that pi r squared is the area of the circle, and theta over 2 pi is a fraction that governs essentially how much of that circle are we looking at for the area. And that will determine the area of the sector. So notice that since we are on the unit circle, we get a radius of 1. And so plugging in, we wind up with r equals 1, makes that essentially go away, but it's still there. And we get pi times theta over 2 pi. If we cancel the pi's on the top and the bottom, since they're obviously non-zero, we get area equals theta over 2. So now you see there is a good reason why we define theta over 2 to be the circular sector. And remember, back in previous slides, we defined cosine to be x equals cosine theta and y equals sine theta. So now notice the argument of the functions cosine and sine, theta. And look at the area, theta over 2. We see that the pattern here is that the argument for the trig function is twice that of the area of the sector of the unit circle. This seems to be pretty interesting. And now that leads us into doing something similar for the unit hyperbola. So again, here's the unit hyperbola, just the right branch of it. As you see, we have to make the area t over 2. Why t? Because again, remember, we cannot get angles at or above 45 degrees or pi over 4 radians. So we say, okay, let t over 2 be the area of this hyperbolic sector, if you will. And the point is cos t comma sinh t. And now we are going to start looking at the area of the unit hyperbola. So we say let t over 2 be the integral from 0 to sinh t of 1/2 times the square root of 1 plus v squared dv minus 1/2 cos t sinh t. So let's take a moment to unpack this formula. So first of all, you would notice t over 2 on the left, because that is the area of this hyperbolic sector that we're interested in. Remember that the geometric interpretation for the integral is just area under a curve. And so why the bounds 0 to sinh t? Well, if we start at y equals 0 and we integrate up in the vertical direction, we find that we start at y equals 0 and at y equals sinh of t. So that is why we get the bounds of the integral to be what they are. Now this 1/2 times the square root of 1 plus v squared dv is a little bit intriguing. Where does that come from? Well, if we draw a line from cosh t comma sinh t to the y-axis and then down to the origin, with obviously the x-axis as the base, and we shade all the area in there, we get the area of this entire thing. But notice that there is a minus 1/2 cosh t sinh t. Why is that? Well, if you see this triangle going from cosh t comma sinh t to the y-axis and down to the origin, this white area is the area of that triangle because the base length is cosh t, height is sinh t. And we know the area of a triangle is half of
That thing right there.
base times height. Yep. Yeah. And so now we are going to try to get t equals something on the right-hand side. First thing first, let's deal with the fractions. If we multiply both sides through by 2, we wind up getting this formula. T equals 2 times the integral from 0 to sinh t of square root of 1 plus v squared dv minus cosh t sinh t. Now it's going to get very clunky, so I'm just going to go through the basics. Now let's just make a substitution, but v equal tangent of u. Then once we do that, we get this formula down here. So remember that if we plug in tangent of u into where the v is, we get 1 plus tangent squared of u, which is equal to secant squared of u by our trig identities. And now, as long as we are going to be positive, which is what we're going to be doing here, restricting ourselves to the first quadrant, this works out to be secant of u. But dv is equal to secant squared of u du. And if we multiply these two together, we get secant cube u du. Now for the bounds. So notice that we have the bounds in terms of v equals. So v equals 0 and v equals sinh of t. Now taking the substitution to the right, we can solve for u and say u equals arctan of v. Again, knowing that we are just in the first quadrant. And so arctangent of 0 is just 0. And the arctangent of sinh of t is just arctan of sinh of t. And everything else stays the same as it is. Now we're going to use integration by parts on the 2 times the integral from 0 to arctan of sinh t secant cube u du. And when we do the integration by parts, we come up with this nasty looking formula. Natural log of absolute value of secant u plus tangent u plus secant u tangent of u from 0 to arctan of sinh of t minus cosh t sinh t. So it looks really nasty, but upon working it out, we get something really nice. The natural log of cosh of t plus sinh of t. Again, we can assume these are positive because we are restricting ourselves to the first quadrant. And so remember back before when we talked about cosh of t equals 1/2 e to the t plus e to the negative t, and sinh of t equals 1/2 e to the t minus e to the negative t. And we were thinking, okay, where do e to the t, e to the negative t, and the 1/2 factor come from? Because how are the exponentials related to those trig identities? But here's the thing, now that we know that t equals the natural log of cosh t plus sinh t, thanks to our handy dandy area parameterization, we can build these. So notice if we exponentiate both sides, we will get e to the t equals cosh t plus sinh t. And to get e to the negative t, all we have to do is substitute in negative t where t is. But now using our odd even knowledge of odd even trig functions, cosh of t is an even function. So cosh of negative t equals cosh of t. And since sinh of t is an odd function, sinh of negative t equals negative sinh of t. Now we're getting closer. What we can do is we can add e to the t plus e to the negative t and get 2 cosh t when we work it out. Also, e to the t minus e to the negative t gives us 2 sinh t when we work it all out. Now you see how close we are to getting cosh t and sinh t. All we have to do is, in each of the two equations, divide by 2, and we find out that the calculus textbooks were right, and cosh t equals 1/2 of e to the t plus e to the negative t, and sinh t equals 1/2 of e to the t minus e to the negative t. So now, thanks to our area parameterization, we understand where these formulas are coming from. Now we're going to move on and talk about the inverse hyperbolic trig integral formula. But before we get there, we are still going to be using area, but to make life easier for us, let's convert the unit hyperbola x squared minus y squared equals 1 into polar coordinates. So remember, from Cartesian to polar, the conversions are x equals r cosine theta, y equals r sine theta. And so we substitute that in and we get that. Now r squared is in common in both terms. So we factor that out and we're left with r squared times cosine squared theta minus sine squared theta equals 1. Dividing both sides by cosine squared theta minus sine squared theta produces this. And dividing the numerator and denominator of that resulting formula gives us r squared equals secant squared theta over 1 minus tangent squared theta. Now you may be asking, wait, how do we know we can divide by cosine squared theta minus sine squared theta? And then again by cosine squared theta, which is an excellent question because yes, if either of those two come out to be 0, we are in trouble. However, notice cosine squared theta minus sine squared theta is equal to 0, i.e. cosine squared theta and sine squared theta are the same when theta equals pi over 4. But notice that we cannot get up to pi over 4. So therefore we are safe dividing there. And cosine squared theta is equal to 0 if theta is pi over 2. Again, we're not even close to pi over 2. So we can just divide and be good. Now we're going to use the area of a figure in polar coordinates, which we know to be a equals 1/2 of the integral from alpha to beta of r squared d theta. And now we are going to put that in. So you see secant squared theta over 1 minus tangent squared theta is r squared, and then the d theta. Now you may be asking, where did the 2 go? Where did the 1/2 go, rather? Notice we wiped out t over 2, which was just the area of the hyperbolic sector, and we multiplied everything through by 2. And so this is where we're getting this formula. Now notice 0 and arctan y over x just represent angles because theta is an angle. So we start at theta equals 0 and go up to arctan of y over x. Now we're going to go through a series of substitutions to get 3 big integrals that are all equivalent to this first one. So using u equal tangent theta, du equals secant squared theta d theta, we get du over 1 minus u squared integral from 0 to y over x. Now the next, so that is integral 1. The next 2 integrals are going to be a little bit tricky yet clever in that we have to do certain substitutions. So I'm not going to take the time to go through them in detail because that would just eat away the time I have. So doing the substitution, we get integral from 0 to y of dv over square root of 1 plus v squared. Doing the substitution over to the right of us will wind up giving us integral from 1 to x of dw over the square root of w squared minus 1. Now we're going to give all of these 3 integrals names. So let's first of all let z equal hyperbolic tangent of t equals y over x. So the second integral here is going to just change just ever so slightly with the bound. So now we're going to get arc cosh of x equal the integral from 1 to x dw over the square root of w squared minus 1. Arc sinh of y be the integral from 0 to y of dv over square root of 1 plus v squared. And arc hyperbolic tangent of z equals integral from 0 to z of du over 1 minus u squared. Now, this is just the way we're defining. But you may ask, why did we go through all this pain to get these integrals? Well, now here's where we're going to use these integrals to actually give us the derivatives of the normal hyperbolic trig functions. So how we're going to do this is we're going to pull in 2 theorems from calculus, the fundamental theorem of calculus and the inverse function theorem. Just a brief refresher, the fundamental theorem of calculus says we have an antiderivative big F, and we differentiate that. Essentially, we're differentiating the integral from a to x of f of t dt with respect to t. But we can slide in the upper bound, x, into this integral and get ourselves little f of x. Then we also know the inverse function theorem, which is the derivative with respect to x of the inverse function of f equals 1 over, for lack of a better way to say it, f prime of f inverse of x. And these two are going to play a crucial role in understanding the derivatives of the hyperbolic trig functions.
Can you go back a slide, Eden?
Yeah.
So isn't this supposed to be dx? So you're differentiating, the integral is a function of x, so you need to be different.
Oh, right. Yep.
So,
Yeah, sorry, my bad.
okay.
So now we're going to take the derivative of y equals sinh of t. So we take the derivative of sinh of t, which in this previous slide is our inverse function. And then our f prime is going to be this arc sinh function because these two undo each other. And we have ddt of sinh t equals 1 over the derivative with respect to y of arc sinh of y, where we evaluate y at sinh of t. Now you may be asking, why do we do that? Well, notice if we did ddt of arc sinh of t, we run into trouble because arc sinh and sinh are just inverses of each other, and that would give us 1. So we are going to leave y here for a moment and then come back and plug in sinh of t later on. So let's roll through. Okay. Notice that arc sinh of y, we have a formula from that based on previous slides, which is this integral right here, integral from 0 to y of dv over square root of 1 plus v squared. Now we're going to slide in the upper integral, since we're differentiating with respect to y, into here and get 1 plus y squared in the denominator. But we can just rewrite it, get rid of all this, and clean up our mess using square root of 1 plus y squared, just reciprocating the denominator. And notice we're evaluating at y equals sinh of t. Now, here comes the tricky part. Notice 1 plus y squared. Doesn't that look familiar? Well, remember the unit hyperbola, x squared minus y squared equals 1. So if we rearrange to solve for x squared, we get the form 1 plus y squared. Aha, that is exactly what we have down here. And we know since we define x to be cosh t and y to be sinh t, we get cosh squared t equals 1 plus sinh squared t. And now, once we do that, we'll end up getting, when we plug in sinh of t, and for y, we get 1 plus sinh squared of t square rooted. That gives us squared cosh squared of t square rooted. And since we are assuming we are in the first quadrant, we get cosh of t. So there you have it. The derivative of sinh t is equal to cosh of t. And now we can get the following, as I said earlier, but using similar arguments, we can get that the cosh prime of t equals sinh of t, and the derivative of hyperbolic tangent of t equals hyperbolic secant squared of t. Now, we're only considering the first quadrant, but Caleb will talk about other quadrants. And for like the fourth quadrant, for example, this argument will still work. We just have to change how we view it slightly, but it winds up working. And notice this, we never even use the analytical formulae, not once, not ever. And so this gives us confidence that yes, when the calculus textbook goes through and derives using the analytical formulae, you get the same thing. But now we understand with the area approach, geometrically, why we get these. So we've covered a lot of ground. We covered what are hyperbolics. We've looked at the relationship to the polars, parameterized both of them by area. And then we just saw the logical consequences that came from that, such as why to formula what they are, the integrals, and the derivatives. So now I want to close with this extension. There's another class of trigonometric functions out there called the Lemniscate functions. Lemniscate looks like a figure 8, and we can just plot it on a graph. Here's the thing, we can't use what we know about like, oh, how do we look at cosine theta, sine theta? Because again, once you get up to theta over 2, well, weird stuff starts happening. We also can't parameterize by area, because if we ran a line through this foci to be the x-axis, notice after a certain point, we are starting to accumulate negative area, and that screws up the entire calculation. But what if we could parameterize by arc length? Then we might be able to bypass these issues. And no one has looked into this in great detail yet, so I encourage you to think about it. It's going to be interesting. And if you find out, hey, parameterizing by arc length works, well then what about parameterizing the hyperbola by arc length? If that works too, then maybe we can parameterize the polar functions by arc length. If we have that, we see, the underlying link between polar, hyperbolic, and lemniscate functions is the arc length. Thank you.
Right. So I have a couple questions.
Yes.
So any questions? I'll let other people ask questions if they have. I know some people are watching online, but any other questions?
System reference.
I have a quick question.
Yeah.
Could you go back to the slide where you were initially talking about the area of a hyperbolic?
Yes. So like this.
Yes.
Yeah.
Where did the 2 come from in the second line?
The 2 in the second.
Because you're multiplying by 2 on the right side and you have a half on both those terms. It seems like there shouldn't be a half in front of square root of 1 plus v squared or something.
Yeah, upon looking at that, you're right. Yeah, my bad. So that should be just
I think this should just not be here.
the 1/2. Yeah.
So that should not be there. So
Yeah,
for
okay.
instance,
So
if you go to the previous slide, so go to the previous slide.
Yep. On that. Oh,
Okay, so
there we go.
you know that this thing is x squared minus y squared equals 1. Right?
Yes. Yep.
And so you know that if you want this total area right
Mhm.
here, how would you do that? Well, you would kind of integrate along the y-axis,
Mhm.
right?
Yep.
So what you would do is you would solve for x. So x is like equal to square root of 1 plus y squared or something, yes.
Mhm.
And then, so you would go the integral from 0 to where? What's the y coordinate where we stop this nonsense?
Sinh of t.
Yeah, from 0 to sinh of t. And it's probably not good form to use x here. So
Yeah.
it would be the square root of, that's why we put 1 plus
Plus
b
b.
squared
Mhm.
db. But then if you want to get rid of this junk right here, you have to subtract off. You have to subtract off the area of that triangle,
Right.
which has base, or height sinh t and base length cos t. So
Mhm.
it's minus 1/2 cos t.
Right.
Sinh t.
Yep.
So that's where that area, and of course that area that's left is just this thing right here, right?
Yep.
So then you know that that's got to be 2 over 2. Yeah.
Yep.
Cool. I think I had a question. Do you have any other questions, Caleb? Or anybody else? So I think I had a question. So can you click through some of these again?
Yeah, go forward.
Yeah.
Okay.
Just go. Keep going.
Okay.
What I was thinking. Okay, so t is equal to all of those integrals.
Yes.
T is equal to all of those integrals, and you've defined, so x squared minus y squared is equal to 1, right?
Mm-hmm. Yes.
But you've let x be cos of t.
Yep.
And you've let y be sinh of t.
Yes.
Okay.
Mm-hmm.
And then you've defined like z to just be y over x, right?
Right.
Which y over x is sinh t over cos t, which is
Hyperbolic tangent.
tan t or whatever.
Which, yeah, is similar to, remember,
So-
y over x sine over cosine. It's just tangent.
So what's your motivation then? Like you could have called, right? You could have said, okay, t is equal to any of those integrals.
Yeah.
Why do you just decide arbitrarily to let, do you have to say, for instance, that arc sinh, because after all, think about this. So arc sinh of y is equal to t, right? Just based on that one equation right there.
Yes.
Why do you just arbitrarily decide that arc sinh of y is equal to the integral with the y in it? Could you have also said that arc cos of x is equal to that integral? Like, could you have said that that this is equal to arc cosh of x. You could have said that this integral right here in y is actually arc cosh of x. Could you not have said that? You could have said that,
I
right?
mean, yeah, you could have. I think just for the sake of consistency, we don't want to mess around with like y, x,
Sure, right,
and all
okay.
that.
Right, and you could have written x as the square root, or right, so you would have written arc cosh of, well, what is x? X is the square root of 1 plus y squared, right?
Mhm.
So it would have been like arc cosh, the square root of 1 plus y squared, or something like that.
Yep.
I'm just sitting here thinking about it, like, I think that even if you had, I was just sitting here thinking about it while you were talking,
Right.
which by the way is also just arc sinh of y, correct?
Yes.
So I was sitting here thinking about it and I was like, good night. It seems like even if you just had a single one of these integrals, you could like use the chain rule or something and get the derivative of any one of them. If you had even just one of those,
Yeah.
like the one within y,
Mhm.
you could re-express it as the arc cosh. I'm not sure about the arc sinh though. That might be tricky. Could you do it? Well, I mean, you could say it's arc tangent, arc hyperbolic tangent of z, but that has a y and an x in it. That's sort of gnarly. Well, although I guess you could have re-expressed y as like, I don't know, yeah. So you would have arc hyperbolic tangent of y over x is equal to that integral 0 to y over x or something. But
Yeah.
it seems like if you had even one of these, you could figure out what the various derivatives were.
Right. Yeah. And that's the nice thing about these integrals is we can find the derivatives of normal hyperbolic trig functions without using, like, say, the formula 1/2 e to the t plus e to the negative t.
Yeah.
And doing all that mess. So it turns out to be a lot simpler.
Right.
And more rewarding too.
Yeah. By the way, those substitutions, I knew how to do the first one. And I knew it was going to work at that point. But then I didn't know how to get the other ones. And so that's when I called my friend John and I said, hey man, these all have to be equal to these other integrals. They just have to be. Because they're all equal to the arc hyperbolics. It took him a while to kind of catch up, just because he didn't know what I was talking about at first, obviously. But then after about a week, he came back and said, oh, I see what's going on. And then he had these crazy substitutions too that he'd come up with. And I was like, oh, in the world.
Yeah, I work them out there. They're long and painful, but hey, they get the job done. So.
Yeah. Well, cool. Thank you, Enoch.
Yeah.
All right.
Thank you. Yeah. All right. I'll get you yours.
All right, so my presentation, as Enoch kind of mentioned, is like a follow-up on the paper that he just presented on. So the paper that I'm going to be talking about is Inextricably Linked, a Trigonometric Coupling by John Egbers, our very own Adam Hammett, and Ian Hogan. So the motivation behind this paper is similar to the motivation behind Enoch's paper. Hyperbolic trig hardly receives a fleeting mention, while polar trigonometry gets all the attention. As it turns out, however, these two trigonometric paradigms are fundamentally coupled in what the authors call is a rather elementary way. And it actually is rather elementary. So a lot of the things that Enoch talked about, I'm going to assume that you kind of know at this point. So for example, parameterization by area. Enoch did a great job talking about kind of the motivation behind why we think about area. So for the purposes of this presentation, we're going to be talking about the polar and hyperbolic trig functions in terms of the area parameters theta and t, just like Enoch did. Okay, so let's start thinking about this. So initially, we're going to consider points in the subset S of R2 defined by
xy such that x is greater than y is greater than or equal to 0. So a way of visualizing this is picturing the first quadrant, the line y equals x in that first quadrant, and the set S is all the points that are below the line y equals x and above and including the x-axis, okay? So this is like below or including the right branch of the unit hyperbola, right? So it's below the asymptote, but non-negative to agree with some integration stuff we're going to do later. So consider a point xy in this subset of R2. We know that this point lies on a unique circle, x squared plus y squared equals r squared. And so it has a polar coordinate representation. Xy is r cosine theta, r sine theta. This is no surprise to any of you. This is just what you learned in Calc 2 and probably before that. But here's where it gets interesting. This point also lies on a unique hyperbola, x squared minus y squared equals rho squared. And so it has a hyperbolic coordinate representation, xy equals rho cos t, rho sinh t, okay? So we're going to be talking about these two coordinate systems throughout the rest of this presentation, and it's kind of going to be the backbone behind everything that we do. So one of the first results that we can find is these 5 identities here, okay? So this kind of relates polar coordinates and hyperbolic coordinates, and it tells you kind of how to convert between the two of them. So this is basically the definition of polar and hyperbolic trig, like x equals r cosine theta, which equals rho cos t, okay? So you can convert in that way. So the rest of the identities are similar to that. And Enoch actually mentioned 1D, so that's pretty easy to derive. So all these identities I'm going to be referencing throughout this presentation. So kind of to give a little bit of motivation, I'm going to start off with an example. So we're going to parameterize the unit circle and the unit hyperbola in their opposite coordinate representations, okay? So let's start with a point xy on the unit hyperbola, cos t sinh t, in the subset that we're dealing with. So relation 1b on the previous slide tells us that r squared cosine theta minus sine theta is rho squared, but that's equal to 1 because we're on the unit hyperbola. Rearranging that, we end up with equation 2 right there, which is the hyperbolic coordinate representation of the unit circle, okay? Okay, so given xy on the unit circle, we're going to, oh, wait, I'm sorry, I made a mistake. So this is actually, equation 2 is the polar representation of the unit hyperbola. I'm sorry, yeah. So this right here is the hyperbolic representation of the unit circle, okay? So we start with a point xy on the unit circle, and we use the identities on the previous page, and we end up with equation 3 right there, okay? So we're going to use equation 2 and 3, mostly equation 3, throughout the rest of this presentation. So here's kind of our logical starting point, all right? So we're going to assume the following 6 facts about polar and hyperbolic trig. So P1 and P2, the derivatives of sine and cosine, those are pretty easy to accept, right? We all know that derivative of sine is cosine and the derivative of cosine is negative sine. P3, Enoch actually mentioned this. This is just something you learn in Calc 2, that the area of a polar region is just a half the integral from alpha to beta of r squared d theta. Also pretty easy to accept, and you can argue it geometrically exactly why that's the case. Okay, there are actually hyperbolic trig analogs to these polar facts. So we're going to call these H1, H2, and H3. So H1 is that the derivative of sinh t is cos t. H2, the derivative of cos t is sinh t. Those are pretty easy to accept. H3 is a little bit more obscure though. So the area of a region bounded by some hyperbolic curve between A and B is that integral, which is oddly similar to the polar integral over on the left side, right? So the authors go into a little bit of detail as to why exactly that's the case. They actually tell you about why the differential dt is the way that it is, or rho squared dt rather. So I'm not going to go into exactly why that's the case, but I'm going to give an example that'll maybe motivate why that equation is the way that it is. So we're going to find the area of a polar sector using that hyperbolic integral formula, okay? So we're going to let theta naught be an angle between 0 and pi over 4. So that's kind of below the line y equals x to be in the correct domain. And we're going to consider the unit polar sector with vertex angle theta naught. Okay. By relation 1c, a couple slides ago, there exists a unique t naught at least 0, such that the hyperbolic tangent of t naught equals the tangent of theta naught. So this means that we can write the polar interval 0 to theta naught as 0 to t naught, but t naught is equal to the arctangent of the tangent of theta naught by that equation that I just showed you. So using this fact and h1 to h3 and equation 3, which was the hyperbolic representation of the unit circle, the area A of our unit polar sector is this mess. So this is just h3, right? This is the hyperbolic integral formula for that hyperbolic region from the bounds that we just found of the hyperbolic representation of the unit circle with respect to t. So we're going to make a substitution, a pretty easy one, u equals hyperbolic tangent of t, and we end up with the second integral right there. And the astute among you, you may not even have to be that astute to notice that that's just the arctangent of u from 0 to theta naught, okay? And if we end up doing that integration, we end up with theta naught over 2, which is the area of a polar sector in the of a unit polar sector with angle theta naught, okay? So hopefully that gives you a little bit of motivation as to why exactly H3 is the way that it is. Okay, so Enoch talked about how you can start with some polar trig facts and get to the inverse hyperbolic trig functions and their integral representations. I'm going to go the other way. I'm going to start with hyperbolic trig facts and get to the inverse polar trig integral formulas. So we're going to start with a point on the unit circle. So h1 to h3 and equation 3 tells us that theta over 2 is that integral. This is very similar to the example that I just showed you, okay? So we're just going to rearrange this a little bit. Theta is equal to 0. The integral from 0 to the inverse hyperbolic tangent of y over x of the hyperbolic representation of the unit circle.
Can I ask you real quick, Caleb?
Yeah,
What's
sure.
Equation 3, I know what h1 through h3 are.
Yeah, equation 3 is that.
Oh,
there.
right. Okay,
Yeah.
so you just parametrized.
The unit circle
unit
in terms of
circle.
hyperbolic
Okay,
coordinates.
yeah. Okay.
There you go. Okay, so we're going to make the same substitution as we did in the previous example, and we end up with this blue integral. And it's blue because it's important. And I'll show you why it's important on the next page. We'll make another substitution. This looks kind of similar to what Enoch did. And a third substitution that gives these 3 blue integrals all equal to theta. Okay, so I'm skipping over a lot of algebra here. It's kind of mundane, but that's just to save some time. So relations 1a to 1c, which is just kind of how to convert between polar and hyperbolic coordinates, tell us that theta is the arc cosine of x, is the arc sine of y, is the arctangent of y over x. And Dr. Hanneman kind of talked about why that is kind of at the end of Enoch's presentation. But we found that theta was equal to these 3 integrals right here. So we can say that the arc cosine of x is the integral from 0 to x negative ds over root 1 minus x squared, and those other 2 integrals right over there. Okay, so this is really important. That's equation number 4. Equation number 5 right there is what Enoch showed in the previous presentation. So you just do a similar approach starting with polar facts, and you can derive the inverse hyperbolic trig functions, their integral representations. So at this point in the paper, the authors talk about how we actually don't need to be restricted to S, the subset of the XY plane that I defined at the beginning. I do not have time to talk about exactly why that is. I can talk about it later if you want. But basically, we can assume from this point forward that these integral formulas, especially the ones number 4, are defined on their usual domains. Okay, so we're kind of moving on from the subset S of R2 that we defined at the beginning. So our goal now is to obtain the derivatives of the polar and hyperbolic trig functions using these integral formulas that I just showed here. And we're going to actually start by moving on from T as an area representation. So it can be shown that basically cos T is even and sinh T is odd. Okay, the authors show precisely why this is. So this means that you can actually take any point in the XY plane and relate it to the first quadrant, right? So you can take sinh of negative t and kind of turn it into negative sinh of regular t. So this means that the basic hyperbolic trig functions are actually defined for all t in R, okay? So we can do a similar thing for theta. Up until this point, we've been thinking of theta as in the interval 0 to 2 pi as an area parameter. So if we have an angle or a theta that's outside of 0 to 2 pi, all we have to do is just find an integer a such that theta plus 2 pi a is in 0 to 2 pi. So this means that any angle we're given, we can kind of convert it back into the interval 0 to 2 pi. So the basic polar trig functions are also defined for all theta in R.
By the way, that forces sine and cosine to be periodic.
That's correct. Yes, and yes, you guys mentioned
If
that.
you didn't know that, but I mean, like, if you didn't know anything about sine and cosine, you just defined it in terms of the area parameter and did this, it forces them to be periodic.
That's correct. That's right. Okay, so I'm skipping over a lot of details here in lieu of time, but we can apply the fundamental theorem of calculus and the inverse function theorem, like Enoch detailed in the last presentation, to equations 5. And remember, equation 5 were these inverse hyperbolic trig functions. So this is exactly what Enoch did. He found that these derivatives are actually what they are. Okay, so the derivative of sinh is cosh, derivative of cosh is sinh, and the last tant derivative. There's a slight problem with this, especially with 6b. So in equation 6b, we're applying the inverse function theorem with f inverse being cosh t and f of t being the inverse cosh of t. But cosh t is even, which means that it only has an inverse for t greater than or equal to 0. Okay, so the inverse function theorem actually only guarantees that the derivative of cosh is sinh for t greater than 0. Okay, so let's fix this. We want it to be defined for all t. Well, it turns out if t is not equal to 0, 6a and 6c actually imply that the derivative of cosh is the derivative of sinh, right? So we just turn cosh into in terms of sinh and tant, which we know are defined for all t in R. And we can find that for all t not equal to 0, 6b does hold. But what about for t equals 0? Well, it gets a little bit gnarly. So the authors actually use the mean value theorem at this point, which I thought was kind of exciting. So think of some h greater than 0. It could actually be less than 0 too, but just to agree with interval notation, I chose it to be greater than 0. Cosh t is continuous on the closed interval from 0 to h, and it's differentiable on the open interval from 0 to h. That's what we just showed, right? So this actually means we can apply the mean value theorem. So the mean value theorem guarantees that the difference quotient, cosh of h minus cosh of 0 over h, is the derivative of cosh at some point in the open interval from 0 to h. Okay, and we call that point xh. So, right, we know that this is true by the mean value theorem. Well, it turns out if you just take the limit as h goes to 0, by continuity, this approaches the hyperbolic sign of 0, right? So 6b actually holds for t equals 0 by the mean value theorem. So we've concluded that all three of these derivatives do in fact hold for all t in R. So that's kind of an interesting detail. And we can do a very, very similar procedure and find, starting with the inverse hyperbolic integral representations, and we can derive that the derivatives of the polar trig functions are what they are. We have to use the mean value theorem too, but that's kind of interesting. So what on earth did I just do? Well, we have shown that if we start with P1 to P3, right, the basic polar trig facts that we started with, we actually get H1 and H2 for free. Okay, so the P1 to P3 imply H1 and H2. And H3, which was that weird hyperbolic integral formula for area, can be argued geometrically, and the authors do that in the paper. And if we start with H1 to H3, we actually get P1 and P2 for free. They imply. And P3, again, can be argued geometrically. So these two trigonometric paradigms kind of imply one another. So they are inextricably linked. All right. Thank you.
So any questions from from Zoom. A few people on there. Questions there?
No question.
Enoch, do you have any questions?
Yeah, so if you go back to like the proofs slide,
This one?
yeah.
Okay.
So I'm just wondering why you like put like S. Is that just because like the fundamental theorem of calculus?
Well, we just want to name it something,
Okay,
right?
okay.
So on the previous slide, we had different variables. We had U, V, and W, but we don't need to call them U, V, and W.
Right.
So we just want them to be different from the upper bound of the integral.
Right.
So as long as it's not that, then we're fine.
Right. Otherwise, you have to invent a whole bunch of variables.
That's right.
V, W, and then you start running out of stuff pretty quick.
Yeah, that's right.
Yeah, oh wait, yeah, equation for, that is familiar, that is what we were taught, like, was it right, like the derivative of like arc cost is going to be like negative ds over square root of
Well,
1 minus this.
the derivative of arc cosine of x is -1 over
Negative
the square root
right.
of 1 minus x squared.
Right, yeah.
Which comes if you apply the fundamental theorem of calculus to that.
Okay, so that's why they were, as we were taught, I think, back at Calc, that's this thing.
So I mean, yeah, the weird thing is you know literally nothing about the inverse trig functions. But you're just able to use geometry and the and like the hyperbolic geometry to get an integral that tells you what the value of arc cosine of x is.
That's
in
right.
Integral form.
Yeah.
Well, once you have that, then you can just you can start doing all kinds of stuff without knowing anything about the inverse arc trig functions.
That's right.
So
Pretty
same
amazing.
thing for the arc hyperbolic trig functions.
Yep.
And again, like Enoch said, that guy Ian Hogan, he kind of came into the project sort of late. Most of this project I thought of when I was sleeping one night. And then all of a sudden I realized, holy mackerel, I think there's an area formula for hyperbolics. It's the same as the polar one. And I started thinking about how to parameterize using hyperbolas and circles at the same time. There's that one picture in the paper that kind of summarizes.
That's
the whole
right.
thing.
Yeah.
But then I just started going crazy trying to write it all down because it seemed I didn't even know what I was doing. I thought that I was proving that the two systems were equivalent to each other, but I didn't know how to even do that. I was like, how do I show that they're equivalent? And what's going on here? And then it was Ian. Okay, so it was Ian who was able to give a rigorous argument for why the area formula worked. I kind of knew that it was going to work, but I didn't know how to write it down. And then I didn't know how to fix all that junk with the derivatives, like we in the original paper that Enoch talked about, it really only applies to like a small proportion of the actual values of those functions.
Yeah.
But the reality is you can fix it by just thinking carefully about how to extend those functions and then using the mean value theorem.
That's right.
And I didn't know how to do all of that. The mean value theorem idea was John's. So John came in later on. At one point, me and Ian kind of were just disagreeing about stuff because he didn't want to write any of that stuff out. He was like, just forget about it. Just say they can figure it out. And I was like, yeah, but I mean, they're not going to. I mean, I've been thinking about this for years, and I'm just now starting to think about this. So I want to actually write it down. And so John was able to kind of plug that gap. And there were some complicated things too about flipping things around where you had to realize pi was some kind of integral, so you flip things around.
That's right. Yeah.
That was a little bit tricky as well. I did that part, but John mainly helped us with the last part of this paper, which was pretty helpful.
Yeah.
But I watched Ian give a talk one time. The reason I invited him into this project at all was I watched him give a talk on limnoscale sine and cosine. And he was parametrizing them by arc length, not knowing anything about any of this stuff. And it occurred to me, oh, there's probably some kind of triplicate connection between all three of those trigonometric paradigms, where you would parameterize these things by arc length. I just haven't really had time to think about it, but I think that it has to work. Where the parameters would all be in terms of arc length instead of area like we did here.
That's right.
So, yeah.
I'd be interested.
Yeah. I want to think about it again now that you brought it up.
There you go.
I don't remember when this paper came out. It was just like
A couple of years ago, or maybe even less than that. Yeah.
maybe it was just last year.
Yeah. Right.
But I haven't thought about it for a while, but I'm sure it's possible. Any other questions? Okay, well, I think next week, Trevor and Claire will be back. I think I don't think Claire talks. Well, maybe she talks next week. I'm not sure. There's a
Yeah, she does. I remember on the Canvas page.
okay, yeah. So it might be Claire and Trevor, and maybe Abigail or something. I'm not sure. I think those three might be presenting next week. So
Yeah.
interesting. And those won't be connected the way that these two.
Yeah.
All right. Cool.
Yeah. I'm glad we got to talk on the same day. That was
Yeah.
kind of interesting.
Yeah.
Yeah. Cool.
I mean, I wanted to, but then you moved. I'm like, okay. And then like Dr. Hammond's like, oh yeah, would you be willing to like, so I'm like, of course, yeah. Then we still get to talk on the same day, so it worked out great.
It did work out.
We
All
just
right.
flipped with the other three.
All right, I'm gonna stop recording this. I'll put this on